This video is made for education purpose only. So we are going to study today about the Haworth projection. So before moving to Haworth projection, we should understand first what is meant by acetal, hemiacetal and hydrate. When we react any carbonyl compound with water, then what happens? It gives its hydrate. Okay? There is R dash, this is R dash. This R dash is equal to H or alkyl or alkyl. If it is H, we know it is aldehyde. If it is alkyl and aryl, then it becomes a ketone. Okay. So this we have already studied in the previous year, and in this picture we are going to study only the what is meant by hydrate. Okay. Then when this ketone reacts with alcohol R second prime OH with 1 mole, whatever we get, that is R2 prime, here is R dash, and this acetal, this is called, this is a hemiacetal. If you react this with 2 moles of alcohol, then whatever you get, that is acetal. Okay, these are the acetals. Now we will move. This is hydrate, this is hemiacetal, and this is a acetal. Once we understand the hydrate, hemiacetal and acetal, we are moving further to the cyclic structure of glucose. We know what is the Fischer projection formula, or we have studied the Fischer projection formula. In this lecture, we are moving to the Haworth projection formula. In order to avoid unrealistic bended linkages in the Fischer projection, in the 1929, Norman Haworth suggested a representation in which the ring is oriented almost perpendicular to the plane of the paper. So you know that what is the Fischer projection formula or general glucose formula? We know that we should write this CHO, there is OH, this side is H, this side OH, H, C, here is OH, H, C, OH here is H, and CH2OH. This is the formula for D-glucose. Okay, this is the formula for D-glucose. If you write in a Haworth formula, in the Fischer projection formula, how we can write? Here is just linear line, here is the CHO, here OH, here is H, OH, H, OH here, H, OH here, and here CH2OH. This is a Fischer projection formula. Fischer projection formula for D-glucose. So what we have to do? We have to convert this Fischer projection formula into the Haworth projection formula. How will you do that? Just you make it the simplest way I am telling you, to make it instead of vertical, write this in a horizontal way. So right here is the CHO. Okay, that's right. top end is going to the right hand side, whereas here is the lower end is at the left hand side. Okay, then you write this H is above, OH is below. Here OH is above, here is H, OH here is H, here is OH, and here is H. So what you have to do, the reaction or the cyclization takes place, this aldehyde can be written like this also, and this OH can be written like this. Okay, the attack of this OH over here, this is carbon number 1, 2, 3, 4, 5 and 6. The hydroxy group present on the carbon number 5 attacks on the carbon number 1, that is the aldehyde carbon, formyl carbon we can say. So what happens? It gets cyclized. So how it gets cyclized? Okay, just you remove this, and here is the O, you can write as such, and here this bond is getting broken. Okay, and here is the OH. So the hydroxy group, we know that in the last year we have studied, what we have studied, the carbonyl group is having two phases. So the attack of the nucleophile on this carbon can be from lower side or from the upper side. In this case, the same way, if the attack is occurring from a lower side, what will happen? This OH will goes up. OH will goes up and hydrogen comes down. Okay, this part is remaining. If this OH attacks from the other side, this OH comes down and this is hydrogen comes up. So what it indicates, there is the formation of one more stereogenic center, which indicates there is a one more stereogenic center formation, which can indicate if the hydroxy is on upper side, it indicates this is the beta. If this is on lower side, it is indicated alpha. Okay, so this is, then how we can write the cyclic structure. So one more important thing I forgot to mention here, whatever is present on the left side of this structure is coming up on the horizontal structure. Whatever is here on the right hand substituent, that is coming on here. Okay, this is the presentation or the representation of this structure. Once we got this structure, then how we can draw the cyclic structure, that we will see. Means cyclic structure means what? That is the Haworth projection or the Haworth structure drawing. Okay, how we can draw that structure, we will see here. Now, what you do? Always you have to put this oxygen on the right hand side corner. Here is carbon number 2 and carbon number 3. Sorry, carbon number 2 is on this side because this is the oxygen side. The carbon number is 2 and carbon number is 3. So whatever the substituent on the upper side, just write on the up. Whatever the substituent on the lower side, just write on the lower side. Okay. Okay. So this, the position at this one is a fluctuating, so it can be written like this. Okay, this hydroxy on the carbon number 1. On the carbon number 2, hydroxy is down and hydrogen is up. On the third carbon, this is up and this is a down. On the fourth, that is a down one, and here is a hydrogen. Okay, on the fifth carbon, what is there? Here is a CH2OH and here is a CH. Okay, so in this case, what we know, if this hydroxy, I will write this on one more structure for this. The same structure I am drawing, only the difference I am going to tell over here. Okay, so here is the OH, here is the H, OH, H, OH, hydrogen, CH2OH, and the H. And here it was, I showed in the wedge line, but here I am showing this hydroxy at the top, and here is the hydrogen. One compound, the another compound in the same way, draw this structure again. Here is the OH, here is the OH, H, and this is OH, this is the OH, here is the H, here is the OH, here is the H, OH, H, H, and here CH2OH. See, the hydroxy on this side and on CH2 on this side. This here, the hydroxy on this side and CH2OH on the same side. So, when this CH2OH and this OH on the same side, then that is a beta. If CH2OH and this OH are on the opposite side, then that is a alpha. So, what is this alpha and beta? Because here generated new chiral center, and this alpha and beta is a nomenclature given for the anomer. Anomer means what? The carbon atom which is present near to the oxygen and having some orientation like alpha or beta anomer. Okay, this is about the alpha beta anomers. Now we are going to discuss about how to draw the chiral chair form and boat form. We know chair form is more stable than the boat form. Now in the chair form, so how we can draw the chair form? So while drawing the chair form, we must know this oxygen is always on this side. Then this simplest way I am telling to draw the structure. Okay, got it? Then this is the chair. Now I erase that structure of glucose once again. I will draw this. Okay. Which side is OH? Here is the OH. Here is the OH. OH. CH2OH. And suppose here is the OH and here is the H. Here is the H. Here is the H. Here is the H. And here also the H. Then how to draw this? Because it is having axial equatorial, axial and equatorial, axial, equatorial and axial. So these are the two substituents, okay, on each carbon. Okay, so whatever the substituents are downside, always represent on the down facing. Okay, this is OH, this is H, this is carbon number 1. Okay, one moment. This is carbon number 1. Here is carbon number. This is equatorial axial. This is carbon number 1, 2, 3, 4, 5, and this is a 6 member. Okay. Now this is a carbon number 1. Hydroxy is on this side. Here is hydrogen on lower side. And on the carbon number, again hydroxy down. Here is the hydrogen. Here this is the OH on the carbon number 3. 1, 2, 3. On the carbon number 4, OH is down and the H is up. On the carbon number 5, here is the CH2. Okay, so this is the cyclic representation of the glucose. Suppose you have, this is a beta anomer. If you have this change, if you have an alpha anomer, OH is down and hydrogen is up, then in that case, what you have to do, you have to write OH at this equatorial position and hydrogen on the axis position. So this is about the aldoses. In case of ketones, what will be there? So this is the case about the aldoses. In the case of ketones, you can see, take the example of fructose. So you write the structure of fructose first. What is the structure of the fructose? CH2OH. Here is the CO. Okay. Then CH here OH. Right. Then COH here and H. Carbon number 1, 2, 3, 4. And carbon number 5 and then last CH2OH. On the carbon number 5, here is the OH and here is the H. Okay. Then, in the previous structure, in case of aldoses, we have seen there is the formation of, in case of aldoses, there is the formation of pyranidine, tetrahydropyranidine. In case of ketones, you can see furanidine, that is a tetrahydrofuranidine. So, pyranidine is what? Where you have a 6-membered ring. In case of furan, you have a 5-membered ring. This is a furan and this is a pyran. Okay? So, this has happened in case of aldoses. We offered this ring, we got this ring and when it's cyclized. When in case of ketones, we are getting 5-membered ring. So, how do we get that 5-membered ring? We are going to study that. Now, you have here ketone, the hydroxy group present on carbon number 5. 1, 2, 3, 4, 5. This will attach this carbon. Again, there is a chance to get 2 anomers over here. One is the alpha, another is the beta. So, this attacks, right? Just make it inward, means rotate this structure to clockwise, make it horizontal structure. Write the structure horizontally. Here, write CO, CH2OH, right? Then here H, here is the OH, here is the OH, here is the H, again OH, H, and here CH2OH, right? So, whatever the first what you have to make, you have to make it cyclize, right? Then what will happen if you make it cyclize? In the just 5 minutes before, I told you that this carbonyl is having 2 phases. The attack of this hydroxy may occur both the directions. It may be either this side or that side, and that gives the product whether it is an alpha anomer or the beta anomer. So, if this attacks on this one to make it cyclize, what will happen? So, let's see here. First, while writing the furan structure, the oxygen should be at the top always. The oxygen should be always at the top position. Then, what you have to do? You have to write CH2OH. Here is the CH2OH. We can start from this side. CH2OH, right? We have to start from this side, CH2OH, then here is the H, then here is the OH and H, and here is the OH and H, and this position OH, or this is the CH2OH. So this carbonyl, when this hydroxy attacks on this carbonyl, there is a carbonyl, and this OH form, if it is going that side or this side, it's decided by this OH attack. And if it is coming lower side, this OH coming lower side, then it is an alpha anomer. If this OH goes up, and that is called as beta anomer. So if you write the structure, whatever these are there, they are on the downside. You can see this OHs are from this carbon, then this hydrogen, then this OH, and this OH was involved in the cyclization, so this is the O from this here. Okay, this OH is involved in the cyclization attack, so this H and OH you can find it here. So while writing the next structure, you can see here what you will see, the alpha anomer and the beta anomer. See, this OH going up and CH2OH is down. There is the OH, H, OH, H, and CH2OH. And here is the H. Okay, when this CH2OH and this OH on the same side, then that is called as beta anomer. When this OH on the opposite side of this CH2OH, that is called alpha anomer. Okay, that is alpha anomer, and this is a beta anomer. So in this lecture, what we have studied, the conversion of Fischer projection into the Haworth projection, and the easiest way to write the structure of, or the cyclic structure or the hemiacetal structure of glucose and the D-fructose. So thank you for watching this video, and this video is made for the purpose of education only and only. Thank you.